We have discussed the eigenfunctions, eigenvalues, obtained the expression for time independent Schrodinger wave equation in one dimension, which was further extended to three dimension. What we got the expression for one dimension was d square psi by dx square plus 8 pi square m by h square e minus v into psi. This was the time independent Schrodinger wave equation in one dimension, and further we extended to the particle called the free particle where V is 0, that's potential energy was 0, and we got the energy is E equal to k square h square by 8 pi square m. And we see that for a free particle this energy is arbitrary, it can have any energy. A free particle, a particle said to be free if and only if it is free from any other potential, either it's electric, magnetic, or whatever the other potential, it is free from the potentials. And for such a particle the energy can be any value, arbitrary value, it depends on the mass of the particle. That was the previous class. Now today we will go to explaining the that is we are applying this time independent Schrodinger wave equation to particle in a potential of infinite height. We call it as a particle in a potential of infinite height. See, look at the diagram at the right hand corner, topmost corner. You got see here we use the term potential well. You know the potential, you know well, a deep well. Here it is a potential well of infinite height. You know that. So imagine it is a deep well. Any imagine and imagine that any particle is fallen into the well, deep well. Then it is not easy to take out the particle outside. It's not easy to take the particle outside, isn't it? Because you need to apply a large amount of energy, then only you can take it out. Imagine the well is very deep and deep and deeper, and certainly you require very large amount of energy. So the particle has the very large potential energy. That is therefore outside the potential well, V of x is infinity. And when the particle is within the well, what happens? The particle within the well is has got certain energy, total energy, imagine, and whose energy is not sufficient to come outside of the potential, isn't it? If the particle is trapped in a well, imagine, what do you mean by trapped? If the particle is there trapped in a well means it won't have sufficient energy to take out. So in such a case, for example, imagine an electron going around the nucleus. Electron goes around the nucleus in different orbitals, starting from the innermost K shell, L shell, M, N, and etc. and so on. When you take any atom, the outermost shell electrons are called the valence electrons. Outermost shell electrons are the valence electrons, and they can be easily removed, isn't it? So these valence electrons always play a role in conductivity or in any chemical reaction, and the inertial electrons K, L, M shell, they don't take part in the conductivity or any reactions. If you imagine an electron is tightly bound, you see here in this case electron is tightly bound to the nucleus, there in K shell, L shell, etc. Therefore it is not easy to be removed. Only the valence electrons can be removed. If you imagine an electron is tightly bound to the nucleus, such a case is called the particle in a potential well of infinite. Okay, in classical mechanics, a particle trapped in the potential well is by moving back and forth between the walls of the this well and remains there only. In quantum mechanics, this particular state, the trapped state of the particle is called the bound state. Any particle that is tightly bound to the nucleus is said to be in a potential well of infinite height. I told you, I given the example. Imagine the electron going around the nucleus in definite orbits. If you take inertial electrons, they have been tightly fixed. Okay, this is the case of bound state. Now taken such bound state, you have seen in the previous diagram, that is the well with boundaries x equal to 0 and the other side x equal to L, and the potentials, if you look at the potential within the, that is inside the potential, inside the potential well, the potential energy is 0. We have x is 0 for the inside the potential well. And for outside, the potential energy is infinity. I told you, if this is here, imagine the particle is tightly bound to the system, and you cannot expect the particle to be there outside. That's what the meaning. If you imagine a particle that is tightly bound to the system, you will not expect the same to be outside the region. Therefore, such a situation is called the tightly bound condition situation. Such a configuration of potential in space is called the infinite potential well. Such a situation where the particle is tightly bound to the nucleus is the perfect case of a particle in a infinite potential well. A particle that is bound within the potential well is referred to as, once again, it is a referred to as a particle in a box. Many times, see here, when I say it is in a box, I will consider three dimension. Otherwise, it is only one direction. Okay, a particle is within the bound box means it is a three-dimensional case. As I told you, an example of an electron bound to the. So now, if you take, see what we are doing here is we are trying to find the uh, wave function for the particle that is in the a system. What we are doing, what is our exercise here was, we are trying to get the wave function for the electron that is confined to a particle. So that is we are finding the wave function for the electron that is bound to the atom. Okay, so we have two probabilities, that is the particle may be outside the atom, that's outside the potential well, or particle may be stick to the atom. So two cases are possible, isn't it? So now let us first consider the particle is outside the potential well. Then what happens according to the Schrodinger's equation? That is, if you apply Schrodinger's time independent wave equation, it is d square psi by dx square plus 8 pi square m by h square e minus infinity, because potential energy is infinity outside, therefore I put infinity into psi, that's equal to 0. So this is the Schrodinger's time independent wave equation, a particle outside the potential. Now this equation has to satisfy, mathematically has to satisfy, this equation will satisfy if and only if the wave function outside the potential well is 0, that is psi is 0, and the probability of finding the particle definitely is 0. Then only we say that particle won't exist outside, it is stick on to the atom. So our here what we are trying to find, I again repeat, what we are trying to understand is that we are trying to get the wave function for the electron that is stuck to the atom. Okay, that is inside the potential well. So therefore, this equation will satisfy if and only if probability of finding the particle outside the potential well is 0. What is the other probable case left over? That electron is definitely stuck to the atom. So it is there inside the potential well. So now here I will put V equal to 0. Why I am putting V equal to 0? Imagine electron going around the nucleus is going continuously going around the nucleus. The total energy is always is equal to the kinetic energy and potential energy. So here I limit this potential energy to a smaller value. It is not exactly equal to 0. We will limit this potential to smaller value. Then what is the other energy left over? It's kinetic energy. So you see that electrons going around the nucleus possessing kinetic energy. We will give maximum contribution to the kinetic energy and less contribution to the potential energy. That is the thing here. So I am limiting the values of potential energy to a minimum value. So the minimum value mathematically can be taken as 0. That's what the meaning. Therefore, again you apply the Schrodinger's time independent wave equation, that is d square psi by dx square plus 8 pi square m by h square e minus 0. Here v is 0 since the particle is stick to the atom that is bound to the system. Therefore, psi is 0 minus e minus 0 psi into 0. This is the Schrodinger's equation, particle that is bound. And again, what I did was I rewritten the previous equation by d square psi by dx square plus k square psi into 0, where psi as usual the wave function and k square becomes a constant, that is 8 pi square m e by h square. So this equation d square psi by dx square plus k square psi is equal to 0 is a second order differential equation where psi is complex quantity. If this is such a, if this is the second order differential equation, then the probable solutions, the general solutions of the differential equation will be of the form psi of x is equal to a e to the power of ikx plus b e to the power of minus ikx. So this will be the general solution for a particle that is fixed to the bound state, and here a and b are constant values. See, this is general solution, we don't know the exact solution, this is not the exact solution, this is only a general solution for a differential equation of the above form. A and b are some constant values, and you will see that e ikx and other case e minus ikx. So what it was said in the earlier, if the particle is there stuck to the, when it is tightly bound case, it is moving within the boundaries. You have seen that is well, any particle that is there inside, it is just reflect, it is moving, and you know that electron going around the nucleus, isn't it? So it is moving within the boundary and gets reflected from the boundaries. So one side it is moving, when it meets the walls of the this potential, it has to reverse, isn't it? So it is e to the power minus case. In one direction, the movement of electron in one particular direction, let us say plus x direction, it is e to the power I case. When it gets reflected from the other side, it is e to the power minus case. So it is a reflected one. So now the particle is going between the boundaries x equal to 0 and x equal to, that's how it is going there and sets up a standing waves. I told you here a and b are some constant values. This constant value we don't know right now exactly. These constant values should be evaluated. To evaluate these constants a and b, we use boundary conditions. See, I said psi of x is a e to the power ikx plus b e to the minus ikx. It is only a general solution where a and b are constant. We don't know what the constant values are. If you evaluate these constants, then certainly you will get the correct exact solution for the wave function. Now, let us evaluate a and b, the constant a and b, using the boundary conditions. Now, what do you mean by boundary condition? Imagine the wave is moving. When it comes to the walls, it gets reflected. So at the walls, on the walls, the wave function don't exist. Therefore, psi of x is 0 at x equal to 0. And again it is reflected and comes to the other end. Again it finds a wall, so it gets reflected. So it has traveled a distance x equal to L. Therefore, at the other side of the boundary, again the wave function is 0 at x equal to L. So you got two boundary conditions where the wave functions are 0 at x equal to 0 and as well at x equal to L. So now you apply the first boundary condition, that is psi of x is 0 at x equal to 0 to the above general solution. If you apply to that, left hand side psi of x is equal to 0, that is equal to a into e to the power of ik 0. Now ik dot 0 plus b e to the power of minus ik dot 0. You know that e to the power of 0, ik dot 0 means it is e to the power of 0, a e to the power of 0 plus b e to the power of 0. Now e to the power of 0 is 1, you know that. So therefore, at x equal to 0, is that becomes a plus b, because e to the power ik dot 0 e to the power minus ik dot is 0, they are 1. Therefore, a plus b is equal to 0. Now we will get the constant b is equal to minus a, or a becomes minus b. So they have changed their, the both are same values, but it is opposite of the other one. So now you use this a. Now take this. Therefore, the new, again I can rewrite the general equation psi of x is equal to a within the bracket e to the power ikx, because a is equal to minus b equal to minus a. Therefore, e to the power within the brackets e to the power ikx minus e to the power minus ikx, close the bracket now. So now if you simplify this bracket, that is equal to 2ia sine of kx. How do you get this? You know mathematically, that is e to the power I theta. E to the power I theta is equal to cos theta plus I sin theta. E to the power minus I theta is equal to cos theta minus I sin theta. You know this. Here, theta for me is k into x. Therefore, e to the power I theta, theta is kx. E to the power ikx is equal to cos kx plus I sin kx, isn't it? E to the power ikx is equal to cos kx plus I sin kx. E to the power minus ikx is equal to cos kx minus Sin, I mean, I sin kx. If you subtract these two, you will get the cos, you will get out of the cos and you will get only 2ia sin of kx. You try this, okay? So now the wave function has become psi of x is equal to 2ia sin of kx, where again a is left over, it's a constant, and sin of kx. Now we apply the second boundary condition. When you apply the second boundary condition, that is psi equal to 0, x equal to L, I can rewrite this expression as psi equal to 0, that's equal to 2ia sin of kl. So psi equal to 0 is equal to 2ia sin of kl. And now I can have a equal to 0, isn't it? If I take a equal to 0, the a 0, b is minus of that, so b is also 0, psi of the general solution won't exist. Therefore, a cannot be 0, only sin of kl is 0, so that it balances the mathematical equation. So, you got two things here, a and sin of kl. Either one is sufficient to have the right hand side 0, isn't it? I can't have a equal to 0, I can have only sin of kl equal to 0. So you know from mathematics, if sin of kl is equal to 0, that is what you get, kl is equal to n times pi. Okay, if sin of kl is equal to n times pi. Look at the first expression. Therefore, k is equal to n pi by l. Since sin of kl is 0, that implies that kl is equal to n pi. Therefore, k is equal to n pi by l. Okay, so therefore k, the constant k, becomes n pi by l, where l is the length of the box. And you know that momentum p is given by h by 2 pi into k. The momentum p is given by h by 2 pi into k. H by 2, therefore that is equal to h by 2 pi. K, what you got, k was n pi by l. Therefore it is, to simplify, p becomes nh by 2l. So momentum is equal to nh by 2l. So this is the momentum. Then what is the possible probable energy, possible energies? So you know that I told you, we are already made, the total energy is kinetic energy plus potential energy. Imagine the electron going around the nucleus versus kinetic energy and potential energy. Here in this case we have assumed that particles tightly bound to the nucleus, and we approximated the potential energy almost approximately to be 0. The minimum is we have considered, therefore we put p is equal to 0. So what is left over for energy? It's only the kinetic energy. So therefore such kinetic energy, that kinetic energy is given by p square by 2m. You know that half m is square, multiplied by m and divided by m will give you half m square v square by 2m. Therefore mv is p, therefore it is p square by 2m. Kinetic energy is p square by 2m. You substitute for p now. So p is p square here. So therefore n square h square by l square, and it is 4 pi there, isn't it? 2 is multiplied by, therefore it becomes 8 ml square. So total energy now is equal to, the possible energy for the electron is equal to n square h square by 8 ml square. Here n is integer, isn't it? So you have seen that n is integer. So n can take values 1, 2, 3, 4, 5, 6, etc. Therefore, when n is 1, what you get? E1 is equal to h square by 8 ml square is one energy. What is when n is equal to 2? It means the particle in the second state. So n equal to 1 refers to the lowermost state for the particle. It is the ground state. Actually, it's called ground state. When the particle got energy, it goes to the higher state, you know, from lasers. So it goes to the higher state. So n equal to 2 now. So what the energy of the electron in the n equal to 2 state, that is E2, is equal to 4 times n square, no, it is, so 4 h square by 8 ml square. And when the electron is in the third state, it is E3, 9 times h square by 8 ml square, and so on. Therefore the energy for the particles now, the probable energy for the particle, that electron can have energy only E1, and the next energy is 4 times E1. The next probable energy, it can electron have 9 times E1. The next, that is when the particle is the fourth state, it is 16 times E1. The next one n is 5, so it is 25 times E1, and so on. So here what you see that here, electron can have energies whenever electron occupies a different energy levels, it can have energy only E1. The next probable energy for the electron is 4 times E1. the next probable one is 9 times even, 16 times even, 25 times even, and so on. But you don't see energy values like 3 even, 8 even, 10 even, or 15 even. You don't see like that. So it is the energy, now the energies are discrete, it is fixed. It is either 4 times even, or it is 9 times even, or it is 16 times even, and so on. So energy is fixed. This is called the quantization of energy. Electron can have energy only even, or 4 even, or 9 even, etc., and so on. So this is called the quantization of energy. When a particle is in the lowermost state, what is the lowermost state is possible for the electron? N equal to 1. So n equal to 1 refers to the lowermost state. So E1, that is equal to h square by 8 ml square. This is called the 0 point energy. 0 point energy is the lowermost energy for the particle in its lowermost state. So here this lowermost state has got energy that is equal to some value, some positive value, that is called the 0 point energy. That is called the 0 point energy. That is, under quantum mechanics, the particle sitting in its lowermost energy state does have some positive value for its energy. It is not zero. It is not zero. It has got some positive value, some value for energy. That is called the 0 point energy. Okay. And all other states n greater than 1 are called the excited states. So n equal to 1 represents the ground state, that is E1, that is equal to 0 point energy, that is equal to h square by 8 ml square. For all states n greater than 1 are called the excited states. We have seen that energies for the particles are discrete. They are only E1, 4 E1, 9 E1, 16 E1, and so on. All other values are not allowed. Electron cannot have any other values, only it allows only these values. It is a this distribution of energy, that is the definite values of energy for the electron, is called the quantization of energy. Okay. So now over this discussion, we got the energy. We have understood that electron can have energy in terms of E1, or 4 times E1, 9 times E1, and so on. So we have seen that energy is quantized. But still you are not evaluate, we did not able to get the wave equation for the electron. So since we already got the value of k, what is the value of k? It is n pi by l. So now I'll rewrite the wave function once again. It is psi n is equal to 2i sine of k. It was k x, isn't it? So in place of k I am substituting n pi by l. So I'll rewrite this wave function. Probable wave function is equal to psi of n is equal to 2ia sine of n pi x by l. Still there is a constant. We don't know what the constant value is. This constant value has to be evaluated. Now how to evaluate this constant? That is, we use the normalization technique. We using normalization technique, we will get the value of a. So what is that normalization condition? You have seen in the previous class, it is the integral of minus infinity to plus infinity modulus xi square is equal to 1 is called the normalization condition. So using the normalization condition, it is possible to evaluate the constant a. Okay. So now within the bracket, I mean within the integral, it is general way of writing normal condition is minus infinity to plus infinity. Here it is the boundaries of the wall. So x is 0 to l. X is 0 to l. You have seen in the diagram, x is equal to 0 one side and other side is x l. So the limits are 0 to l. It's with a then modulus of xi square, isn't it? So the modulus xi square, I'll write it as psi into psi star. You know that what is this in the previous class? That's probability. So psi into psi star is that is equal to modulus of xi square. What is this psi and what is that psi star? Psi, if psi is the complex, psi is a wave function, psi star is its conjugate. Now, if you have seen that psi is a complex number, the value of wave function is given by modulus of psi square. When you take this psi into psi star, it will become a real quantity. You know that psi, if psi is equal to a plus ib, psi star is equal to a minus ib, where I goes to minus I, so a minus ib. Then if you take the product of psi into psi star, it is a square plus b square. So it becomes the real quantity. So now if you take the within the integral modulus psi square psi into psi star dx, that is the real quantity. So you take psi n, that is 2ia sin of n pi x by L, and its conjugate is I going to minus I. Therefore, psi n star is equal to 2 minus 2ia sin of n pi x by L. So now you take these two expressions, I mean two expression within the integral, that is you take the product, and if you do the integration, you will get finally the value for a. So you will get the, if you solve this integral, that is psi n along with the psi n star dx is equal to 1, then you will get the value. That value for the constant, that is a is equal to 1 by root of 2n. Now you substitute this value of the constant a into the wave function psi n. If you substitute for this value, you will get I into root of 2 by L sin of n pi x by L. So now you got the wave function. It is free from all other constants a and b, isn't it? So look at the final, the wave function what we got now is the correct, the exact wave function for the electron, that is psi n is equal to I times root of 2 by L sin of n pi x by L. So this is the wave function. And you know that this wave function is I imaginary. You already got I imaginary. You know that a wave function is a complex quantity, so whose probable values are always the conjugate multiplied into that. That is the modulus of psi square. So when n equal to 1, I can write psi 1 is equal to I times root 2 by L sin of n becomes 1 now here pi x by L. When n equal to 2, the second state, psi 2 is equal to I times root of 2 by L sin of 2 pi by L into x. Like that I'll write, kept on writing it. So you have a series of wave functions, psi 1, psi 2, psi 3, psi 4, etc. and so on. So, and their probable values are again psi 1 square, psi 2 square, psi 3 square. These are real quantities now. So, psi is a complex number. You don't see the value you will get only when you multiply it by its conjugate, that is psi 1 square, psi 2 square, psi 3 square. Now, this psi 1, psi 2, psi 3 represents is the probability of finding the particle in the state n equal to 1. Psi 2 square represents, it is the probability of finding the particle in the state 2. Psi 3 square modulus, within modulus, it's the probability of finding the particle in the state 3. These are all real values. So you will get the values for the probabilities. That's how it is. Okay.